Alright, this is 5-1, transformation of functions. So today we're going to be talking about how we visualize what a graph will look like without just plugging in points and having an input-output relationship, because that takes a lot of time. Unless you have like a graphing tool, putting inputs and outputs or graphing singular points takes a lot of time. But it turns out if we understand function transformations, we can graph things without having to do that, and we can graph them with exactly the same amount of accuracy. So first we need to talk about parent functions. Parent functions are basically, they represent a family of functions of the same kind, and they are usually the most basic function of a certain type. So we just spent a lot of time talking about quadratic functions, and this is the quadratic parent function. It's just y equals x squared. There's nothing multiplied by it. There's no plus 4x plus 2. There's no transformations on these, and you'll come to understand sort of what I mean by that. It is just the most basic quadratic function that you can get. And that's what it looks like graphed. This is just the parent function for the linear function, so just a straight line. And the most basic straight line you can get is y equals x. There's also horizontal and vertical lines that are, well, I guess that's another kind of transformation of these ones. So these represent all linear functions. One second. Okay. And then this is another kind of function that you might recognize, and this is an exponential function, specifically 2 exponential function, meaning that the exponential functions are anything with a variable in the power. And this one has a variable in the power, and it's 2, the base is 2. So this is the most basic 2 exponential function. And this is a square root function, the most basic of the square root functions. So here are just some of our parent functions. There are so many more, and we'll actually see a couple of different kinds of functions that sort of deviate from these 4 parent functions today. So really there's a ton of them. These are just 4 of the most probably common ones that you'll see right now in your math careers. So first we also need to talk about function notation. Function notation is just a way that mathematicians use to talk about functions, and it's really useful for being able to communicate what you mean with functions. So this right here is meant to indicate that this is a function of x. So it's using the variable using the variable x. So when we plug things into a function, you can indicate that by putting something else in those parentheses, and it will indicate that's what you're plugging in. Out front we have just the f. This is what sort of I refer to as just the function name. We use them to just sort of to indicate that this function is who it is, essentially. You can use any variable, but usually mathematicians use like f, g, h, sometimes like usually f, g, h. But it's just, we can just talk about a function without having to write the entire function by giving it a name. So that's really useful. Okay, so let's talk about transforming functions, and this is probably the most important section of the notes today. These 2 pages where we're talking about what transformations happen when you do certain things to a function. So I'm using to sort of generalize these rules, I'm using f of x instead of parent functions. So, and I will even write that. This is replacing parent functions. So this plus a thing is just, what it means is we're adding a constant on the end of a function that we already have. So for example, like if our function is x squared, that's one of our parent functions, plus 2 would be this kind of vertical shift transformation. We're just adding a constant on the end of a parent function. So when we do that, when a is positive, so we're adding a constant on the end, it moves the function up. But you can't guess what it happens when it's negative. It moves the function down. I'm cheating with my technology. Moves the function down. So these transformations are vertical, also known as y on the y-axis. Hang on, I'm gonna think of a good place to put this. This is a y-axis shift. And same thing for vertical stretch, that's also a y-axis thing. So this first page, both of these things are y-axis shifts because they're vertical. I'll match colors here. So the transformations that are happening to functions are happening along the y-axis. So it's up and down transformations. And that's because the transformations, or the numbers, the alterations, I guess, that we're making to this function are happening on the outside of the function. So we're changing the output rather than changing the input. So that's how come I'm calling this output transformations. It just means they're changing what comes out of the function after it's already come out. So if you imagine like functions as like a sort of a factory machine or something, right? You put input like numbers and the output comes out. What we're doing is sort of adding an extra machine on the end of it that changes it just a little bit more, like adding 2. Or for example, this one is a multiply by something after it's already come out of the original function. So this one, you are multiplying, and again, remember this is standing in place of a parent function. So an example might be if we're using like x as the parent function. Remember that there's a parent function y equals x. Well, instead of that, we have y equals x, and then we're multiplying the output by something, like 1/2. And I think actually that's our example down there too. So we're multiplying by something, some number. And specific things happen depending on what number you're multiplying it by. If b is negative, if you're multiplying by a negative, it flips the function. I spelled that wrong. Function vertically. So it just flips the function. So the best example I have for this is like when we have concave up and concave down parabolas. That concave down happens because we multiply by a negative. That leading coefficient is a multiplier, a negative multiplier. So this is what's really happening to flip the function upside down. If b is bigger than 1, it stretches the function. By that I mean it changes the output to be more than it was each time it comes out, because we're multiplying it by something. So if we're multiplying by 2, each output will be 2 bigger, and so we're stretching the function up by 2, twice as big. So this is going to help you in a second more than it's helping you now, but when we say like somebody is twice as tall, we're saying that this guy is like literally twice the height of the other one. So we're making changes to the height of the function. Depending on where it was originally, you multiply that by 2 and make it taller. And you'll see that in a second. Actually, you'll see the shorter version. If b is less than 1, meaning a fraction less than 1, so like between 0 and 1, it compresses the function, or squishes it, depending on what word you like better. Compresses the function. Meaning if you have this average size guy and you're saying he's 1/3 of as tall, he's going to be like tiny little man, right? We are compressing him to be shorter vertically. Okay, so we're going to do some examples here. This is for the vertical shift. This is a graph of the parent function y equals x squared. On the same axis, graph x squared minus 3. So the transformation that's happening here is taking away 3 on the outside of the function. So we're going to scoot them vertically. We're going to scoot each point down. So the best way for me to do this is just make points that I recognize and know on this graph, and then move each of them down 3. So I'm going to move this guy 1, 2, 3 down. I'm going to do this in a different color. 3 down. This one 3 down. That one 3 down. This one 3 down. So I have essentially just moved this entire function down 3 on this graph, and then I will graph it again. And that is the horizontal shift of down 3. Easy enough. This is the graph of y equals x, so it's the linear parent function. On the same axis, graph y equals 1/2 of x. So again, we're going back to this less than 1. We are compressing vertically. So right now we have over 1 up 1. That's how tall we are right now. We're going to take that and multiply it by 1/2, which means dividing it in half. And we're going to do that for each of these to get an idea of how this new line looks. So half of this is 1/2, half of 2 is 1, half of 3 is 1.5. Same thing over here, -1/2, -1, and -1.5. And so our new function looks like this, where it's been compressed by 1/2 from what it originally was. Hopefully that makes sense. Okay, we are going to then go into input transformations. So if you go back to that imagining the machine, the function machine, this one we're adding a little section before it gets to the function machine. So we are changing the input before it even gets to the function, which is why all of these transformations happen within the parentheses here, because remember that this is representing the parent function. And what we're doing is we're changing what is, let me change colors here, so it's, there we go. We're changing what happens before it even gets to the function. We're adding something like that changes the input rather than the output. Which changes, so these are, these are x-axis shifts, or changes, they're x-axis changes, because we're changing the input. And input transformations are always do exactly the opposite of what you think they should do. So y-axis ones do exactly what you think they should do, right? You multiply it by 1/2 and it compresses it. You add 2 and it moves it up. These are always the opposite. And you kind of have to play around with input-output relationships to sort of experiment with that to figure out why it does exactly the opposite, and I encourage you to do that. Just take one of these ones that we have that will transform, and plug some things into the original and then plug some things into the modified and see what's happening as you are changing the input. But we are not going to talk about that. I'm going to let you do that if you want to. The horizontal shift happens when you, again, this is the x-axis, nope, x-axis shift. So I'm going to just give us an example here. These are sometimes harder to sort of visualize what's happening with an actual function. So I always go back to quadratics because we're so used to that. But if I have like x squared, what I really have is something squared, right? The function is something squared. And what we're going to do is we're going to change the input to be something like, we're going to like add 2. We're going to add 2 to that function, that x, before it gets squared, which ends up being parentheses, right? This is the parent graph of x squared, and we're going to add 2 inside. And what that does, if c is positive, it shifts it left. And here's where you think it would go right because it's in the positive direction, but it's actually shifting left. Does exactly the opposite of what you think it should. And this shifts it right. So we have the left and the right in opposite places of what you think they should be, and that's just because it's an input transformation. We'll do this before we go on to the next one. So this is the graph of the parent function y equals x to the third power on the same axis, graph y equals x plus 2 to the third power. So we've added 2 inside the function before it gets to the third power. And that means I'm going to just make some points here. You can actually only see these 3 points. These ones doesn't get to the actual point yet. So we'll just use those 2. What we're going to do is we're going to add 2, which actually shifts it to the left. It does shift it to the left that amount. So we're going to shift it 1, 2 to the left. 1, 2 to the left. 1, 2 to the left makes this one here. And that one here. And so our new function will be something like that. X to the third powers, I don't know if you've seen that one before, but it makes this like a funny, it kind of looks like a parabola with one side turned down, but it actually is, it's much more steep than a parabola on both sides. So, interesting one. And so we have shifted it left 2. So what happens if you multiply on the inside of the function or before it gets to the function? Again, this is an x-axis transformation. I'll give you an example here. So if we have, let's use x to the third power because we just saw that one. So if we're using x to the third power, an example might be if we put like 4 inside the parentheses before it's raised to the third power. There. So that's an example with x to the third power. If your value, which we're calling d, is negative, this one actually acts like it should. It actually flips the function horizontally. There we go. Flips the function horizontally. If d is bigger than 1, then this is where it's funny. It compresses the function specifically horizontally. I'm actually going to erase this so that I have room to write horizontally because it's a really long word. Horizontally. It compresses it horizontally, which is important. You might see why in a second. And then this one actually stretches it horizontally. Now at this point, if you are imagining this, you might ask, isn't compressing horizontally the same thing as stretching vertically? I'm going to say that again. Isn't compressing, let me draw a picture while I talk. Isn't like compressing it this direction, which makes it like that, isn't that the same thing as having the function and taking it and stretching it this way and making it like this? The answer is sometimes. For example, on this function, we could simplify this function to be 4 to the third power times x to the third power, which would make 64 x to the third power. So, so really it is the same as multiplying the whole function by 64 and stretching it vertically. But notice that it's not like it stretches it vertically by 4. Those two things are not the same. So it's better to think of these as compressing horizontally or stretching horizontally. Because in some functions it's not the same. In some functions it is, and it stretches it much more than it would compress horizontally. But in other functions, and in some functions it's exactly the same. Like the linear function, stretching vertically and compressing horizontally are exactly the same in linear functions. But a lot of times, in a lot of functions, it's not the same. So it's better to just to know that this is different and it compresses it horizontally or stretches it horizontally. Okay, so let's sort of imagine what this might look like. That is my dog. Okay, so this is the graph of the parent function y equals the square root of x. On the same axis, graph y equals the square root of negative x. So remember, this is a negative. Okay. One second. Alrighty. So this is a negative transformation. Oh, it's not going to let me draw today. We are adding a negative inside of the function, which flips it horizontally. So we need to take this function and flip it horizontally, which means, let me see if my pen will work. It will. So if we flip these two points horizontally, which sort of is around the y-axis here, it makes this function. So this is what it looks like when you flip horizontally. Vertically would be this way. So that's my horizontal flip happening there. Okay, so now we're gonna sum it all up here, and this is really chaotic, and it looks chaotic, and I know that. But sometimes, I mean, you don't only do one transformation. Like, there's not a rule that says you can't do all transformations on a function that you want to. So so sometimes they do actually look like this. So the inside functions I'm going to just highlight pink because so that they match our highlights before. And these are our outside transformations. And this, the D, just like we were talking about before, is the like horizontal flip, stretch, or compress. That's what that one does, right? This one, do that from the top. This one is the horizontal shift. Left or, nope, yeah, left or right. this one is the vertical. That's the multiplying one. So the vertical flip, stretch, compress. And this is the vertical shift, up or down. So you can do all of these things to a function, and still you can figure out what it will look like. So that's kind of a fun thing to do. So let's do some examples here, and I might not do all of these, I will let you finish, but all we're doing right now is identifying the parent function and the transformations. So we're looking at these functions and deciding what kind of function it is, and then we're going to say what's happening to it. Switch this to blue, there we go. So on this first one, our parent function, because it's x to the power of 2, our parent function is y equals x squared. And I'll just call this the parent function. And then we have two things happening to it. We have a plus 3 that's happening inside the function, and a minus 4 that's happening outside the function. So we have a before, an input transformation, and an output transformation, and both of them are shifts. So we have a shift up 3 happening. Nope, not up 3. That's inside the function, so it's either left or right. And because it's plus, I know it's left. Left 3. And this -4 is shifting it down. That's vertical. 4. And those are our two transformations that are happening to this parent function. This one, the parent function is the square root of x. And both of the transformations are happening on the inside of this function. So we have inside 1/2 and inside -3. So that 1/2 compresses the function. Compress. I really don't want to write the whole word, but I will. Horizontally. By half. So we're compressing it to be half this tall. And then the other transformation is a -3, which moves it right. Shift. Right. 3. Hopefully you can see here that both of those are inside of the function, because the function is happening here. That's the square root is the function. So, and then we have this x to the third parent function. Y equals x to the third. And then we have two outside transformations, 1/2 and -5. Or subtract 5, I should say. So the 1/2, because it's outside, it's a vertical compress. Vertical compress by 1/2. And then the -5 is an up or down shift, so definitely down. Shifts down 5. I will do this one and then I will let you finish. The parent function for this one, it's kind of harder to see in exponential functions, but this is a 2 exponential, because it's the base function is 2 to the x. 2 is not a modifier, it's actually part of the parent function, because there's a bunch of exponential parent functions like 3 to the x, 4 to the x, anything really, e to the x. Those are all their own parent functions. And so those 3, 4, e, those are not transformations, they're just the part of the parent function. So the parent function is y equals 2 to the x power. So we actually only have one transformation happening, and it's an inside transformation because it's happening within that function. If you did a -2 on the outside, it would look like -2 out here, or maybe that out there, which is not what's happening. It's on the inside, which means it's a left or right shift, and because it's minus, I know it's a right shift. So we are going to shift it right 2. Okay, I will leave the rest up to you. Let me know if you have questions.